This is Day 1 Notes, States of Matter, and today we're going to be starting the kinetic theory. The word kinetic means motion, so it's the energy of motion. The kinetic theory of matter says that all particles of matter are in constant motion, even in solids, but the movement is so slight that it's hard for anyone to see. The law of conservation of energy states, just like matter, energy is not created or destroyed in a system. It's only changed from one form to another. In class, we're going to do the magic can roll demonstration, which will show the change of potential energy to kinetic energy and back again. We'll also see a YouTube video that describes the movement of gas particles. The kinetic theory of gases. The word gas comes from the Greek word that means chaos. Numerous experiments have led to evidence that suggests the following behaviors of gas particles at an atomic level. And this brings us back to Avogadro. Avogadro did most of his experiments with gas particles, and when he came up with the number 6.02 times 10 to the 23rd for the number of particles in a mole, that is based on gas particles. Gases are made of tiny particles of negligible volume, which means insignificant or very, very small volume. If you packed all the particles together that fill a room, it'd be about 1/1000th or one of the room's actual size. But these particles are spread out and moving at a very fast speed, so they fill the volume of the room. Gas particles are far apart from each other. They don't attract or repel each other. However, there is an attractive force between the particles of solids and liquids. It's what makes a solid and a liquid, is the fact that they're close enough to each other and have a strong enough attraction that they will actually attract and hang on to each other. Gas particles are so far apart, just like if you're holding two magnets far away from each other, there's no attraction between the positive and negative charges. Particles in a gas also move independently of each other. It's why gases fill a container. The gases will move straight away from each other, hit the sides of the container, and then bounce back. The word diffuse means to move out. Gases have no definite volume. They'll just move, hitting the side until they hit the sides of the container. We're going to take a look right now at an example of a PhET simulation, and we're going to look at what particles do when we put them in here. The first word I want to talk about is diffuse. Diffuse just means moving out. So here when we see our gas particles entering the simulation, they're moving to fill the container. You can see they were concentrated at the beginning where the gases come in, and now they've moved in to fill the container. So they've diffused into our container. Gas particles move very fast, thousands of kilometers an hour. And you can see this when a bottle of ammonia is opened. The entire room will eventually smell. The person sitting closest to the bottle of ammonia will smell it first, and then it will spread slowly throughout the room until everyone can smell that ammonia has been opened up in the room. The particles move randomly in small straight lines until they collide with each other and objects in the room. Let's take a look at our PhET simulation and see how the particles actually move. I'm going to reset the simulation here, and I'm going to slow it down a little bit by making our environment colder. So you can see that the individual particles are actually moving in a straight line unless they collide with the sides of our container or each other. The movement is also very random. They don't collect in one side or another. They're just bouncing continually in our container. At no point do they ever lose energy enough to stop. They just continue to move until they hit the container or each other. We call this a random walk. Gas particles will move in a straight line until they collide with another particle and then change direction. In our PhET simulation, you saw that there was random movement and that molecules do travel in straight lines. All the collisions between gas particles are elastic, meaning that they don't stick together. Kinetic energy, which we're going to define as Ke, can be transferred from one particle to another one, but the kinetic energy is never lost. Let's go back to our simulation and take a quick peek at these molecules. And I want you to notice that when they hit another gas molecule, they will actually speed up. They're absorbing energy from the other molecule, and one of those two molecules will speed up as it travels. It'll then hit the side of our container and then return to a more normal speed. Not all of the particles are always moving at the same speed. Some are moving slower and some are moving faster. Gas pressure is caused by the collision of those gas particles with each other and the walls of the container. As the number of collisions increases, the pressure will increase. So anything we do to increase the number of collisions that's happening will increase the pressure within our container. More collisions are going to result if there are more particles in a particular space. As temperature increases, pressure will increase because the particles will collide with each other and the walls of the container more frequently. Let's take a look at gas particle number and the effective temperature or volume on our gas particles. I'm going to reset the simulation and put in just one pump worth of gas. We'll let our pressure come up. You can see that our pressure is listed right here in atmospheres of pressure. So we've pretty much stabilized right here at about, looks like we're at about 0.037 atmospheres of pressure with one volume of gas. I'm going to put in another one here so we can see the difference in the pressure. We'll give that a second to stabilize. Remember, we were at about 0.37. I've put in another measurement of gas. Now, I don't know that I put in exactly the same amount, but you can see that my pressure has now fairly close to doubled. So the more gas particles I have in my simulation, the higher the pressure is. Now let's take a look at the effective volume. So our volume right now is steady at this point, and you can see that my atmospheres of pressure have settled right around about 0.08 atmospheres of pressure. If I make my container larger, the pressure drops because the particles are hitting the walls less frequently. If I push this in, the pressure increases. Those particles are hitting each other and the walls of the container faster. Also notice that my temperature went up. So there is a direct effect on pressure and temperature of a gas. In fact, my pressure went so high that I actually blew the lid off my container. A region of space where no gas pressure is exerted is called a vacuum. Gas pressure is equal to 0, so there are no collisions. And in class, we're going to watch an example of PEEPs in a vacuum. Atmospheric pressure, ATM, is the pressure caused by the air in our atmosphere. This is going to depend on weather and altitude conditions. As altitude increases, atmospheric pressure decreases. Air gets thinner as you go up. If you've traveled in an airplane, you know that as you go up, your ears will usually have trouble equalizing the pressure. You'll have to swallow or chew gum because the pressure is different when the plane is up in the air versus on the ground. Commercial airplanes will pressurize the cabin so that the pressure is similar to what's at ground level, but usually it's not going to be exact. You can't travel in the cargo hold of an airplane unless it's a special segment because the air pressure in the cargo hold is going to be less, and so you're not going to survive very well with the lower air pressure. Standard pressure is the average pressure as measured right at sea level. Standard pressure can equal 3 different quantities. These all represent the same thing, we're just going to use different units. And you can probably guess at this point is that somewhere we're going to be converting from one unit to another. 1 atmosphere is the same as 760 millimeters of mercury. This is also equal to 101.3 kilopascals. These are all just measurements of pressure. 1 atmosphere, millimeters of mercury, and kilopascals are just measurements of pressure. Each of these equals each other. 1 atmosphere equals 760 millimeters of mercury, which equals 101.3 kilopascals. So we're going to use these to do dimensional analysis problems and convert from one thing to the other. These are listed on the back of your periodic table. In class, we're going to do the power of pressure experiment, where we're going to be looking at the power of atmospheric pressure on 2 empty Coca-Cola cans, cold water. We'll use a burner and a hot plate and some tongs. Gas pressure is caused by the simultaneous collision of gas particles. And remember that pressure can be measured in 3 different units. That's going to be atmospheres, kilopascals, and millimeters of mercury. All pressure conversions can be done in one step. The pressure inside of a balloon is 4.1 atmospheres. How many kilopascals is this? We have our known, and we need to convert that to kilopascals. We take our known, and because we're going to be converting to kilopascals, we're going to need to be using a 1 atmosphere to 101.3 kilopascals in our example. The atmosphere has to go on the bottom, and the kilopascal needs to go on the top, so that our atmospheres will cancel off and we'll have 422 kilopascals. Kinetic distribution for gas particles. Well, temperature is really a measure of the amount of kinetic energy a sample of matter has, whether it's a gas, a liquid, or a solid. But not all of the particles in the sample will have the same amount of kinetic energy. Most of the particles will move with an average amount of kinetic energy. As we looked at our example of gas particles, some of them were moving slower, some of them were moving faster, but most of them were moving at about the same average speed. And so we can say that average speed is the temperature of the substance. If we're looking at a graph of this, we would see the speed of the molecules in a warm gas versus a cold gas. This is the speed of the molecules is going to be faster, and this would be the number of molecules moving at that speed. So you can see we kind of have a bell-shaped curve for both of these, with some of our particles moving slower and some of our particles moving faster, whether it's cold or whether it's hot. The speed of the molecules is going to be what we would term the temperature of the substance. So this has a lower temperature and this has a higher temperature. This would be the average temperature or the average speed, so the temperature. Here's the average speed and the temperature. Let's take a look at the effect of heat and cold. So again, I'm just going to put in one measurement of gas particles. And now I'm going to play around with just adding some heat. As I add more and more heat, you can see my temperature going up there in degrees Kelvin. We'll be talking about that. As my temperature goes up and the speed of the molecules goes up, the pressure is also rising, because those molecules are hitting the side of the container more often. So the average speed of these molecules would be measured in 940 Kelvin units. Now I'm going to slow things down a little bit and cool my sample down. You can see my temperature is dropping, and the speed of the molecules is dropping. When I stop here, the average speed of the molecules is 408 degrees Kelvin. So the temperature is directly related to the speed of the molecules, which in our chamber here is also directly related to the pressure. Kinetic energy and temperature. The average kinetic energy is going to be directly proportional to the Kelvin temperature. The formula to calculate temperatures in Kelvin is very simple. Kelvin is, first off, never going to be a negative number. Kelvin will be equal to whatever degrees you have in Celsius plus the number 273. Room temperature is 25 degrees Celsius. What is this in Kelvin? 25 degrees Celsius plus 273 is 298 degrees Kelvin. So you just take your Celsius temperature, add 273 degrees, and that's going to be Kelvin. As temperature decreases, we saw particles move slower and slower. The particles would theoretically stop at 0 degrees Kelvin, which would be absolute zero. This does not happen due to the fact that we have a kinetic energy theory, and the energy and our temperature is related to an average speed of particles. And we're always going to have some that are moving a little faster than the average speed. The temperature, absolute zero, has not yet been reached. Let's see if we can get it to go in our simulation. So I'm going to take these particles and just keep adding the cold, bringing my temperature down lower and lower and lower. And you can see that the particles are going slower and slower and slower. At absolute zeros, these particles would be moving zero. They would have no movement whatsoever. You can see they're still vibrating. They're still traveling in straight lines unless they collide with something or each other. We're down to 5 degrees Kelvin. 4, 3, 2, and 1. We still have movement because we still have some particles that are bouncing into each other and transferring the kinetic energy. These particles are still moving, so that we have not reached absolute zero. Let's talk about standard temperature. Remember, we've been talking about gases when we were talking about the volume of a mole of gas being 22.4 at STP. Well, that stood for standard temperature and pressure. Standard temperature equals 0 degrees Celsius or 273 degrees Kelvin. Since Kelvin is directly proportional to the Kelvin temperature, since KE is directly proportional to Kelvin temperature, the factor by which the kinetic energy increases or decreases can be very easily calculated. If the temperature goes from 200 degrees Kelvin to 400 degrees Kelvin, then the average kinetic energy will double. 400 divided by 200 is 2. You'll always have to put the final temperature over the initial temperature. It doesn't matter if the number is large or small. The final temperature always goes over the initial temperature. We're looking for a proportion. If a temperature goes from 100 to 300 degrees Kelvin, then the average kinetic energy will triple. 300 divided by 100 is 3. If the temperature goes from 300 degrees Kelvin to 100 degrees Kelvin, then the average kinetic energy will be a third of what it was. 100 divided by 300 is a third. If the temperature goes from negative 73 degrees Celsius to 127 degrees Celsius, then the average kinetic energy will do what? Well, first off, we have to stop, because kinetic energy is proportional only to the Kelvin temperature, not degrees Celsius. You have to convert the degrees Celsius to Kelvin in order to figure this out. Negative 73 plus positive 273 equals 200 degrees Kelvin. 127 degrees Celsius plus 273 equals 400 degrees Kelvin. So the average kinetic energy will double. 400 divided by 200 is 2. Well, that was a long note set. We're all set. You're now